Greetings, AP Chemistry students. Today we're going to wrap up our Unit 3 notes. We're going to talk a little bit more about some spectroscopy, and we're going to talk about the Beer-Lambert Law. This slide we already saw yesterday, so we're going to move on to a little bit of math involved with this. So first of all, frequency, which is abbreviated by the Greek letter nu, which is right here. It looks like the letter V. That stands for frequency, and frequency is a measure of waves per second. And it's measured in hertz. And so the typical symbol you'll see in AP Chemistry is the symbol S for second with a -1, meaning per second. Now, the electromagnetic spectrum is when you take every type of electromagnetic radiation and you arrange it from lowest to highest frequency. You may be familiar from the back of an honors chemistry reference tables that you have radio waves and then microwaves and infrared and then visible light. You've got red, orange, yellow, green, blue, and violet, then ultraviolet, X-rays, and gamma rays. Now, frequency and energy are inversely proportional to wavelength. In other words, the larger your wavelength, the fewer waves per second, because all forms of electromagnetic radiation travel at the speed of light. So if you have a really large wavelength, then you're going to have fewer waves passing in a second because they're all moving at the same speed. Also, higher frequency radiation has more energy. And there is this formula that says C equals this little symbol, which is the Greek letter lambda, and then nu. In other words, C, the speed of light, as in E equals mc squared, that C stands for the speed of light, equals this lambda stands for the wavelength, and nu stands for frequency. The speed of light, it's on your reference tables. It's 2.998 times 10 to the 8th meters per second. And that is a constant that we're going to use. So we're going to kind of look at how some calculations will play out with this. So if we're talking about the energy involved, energy equals this letter H, which is Planck's constant, named for the scientist Max Planck, times nu, the frequency. And Planck's constant is 6.626 times 10 to the -34th joule seconds. And if you have joule seconds and then frequency is measured in inverse seconds, when you multiply them together, your energy will be in joules. Right? So those are our two formulas. They're on your reference tables, so make sure you can find them. The speed of light is also on your reference tables. So we're going to look at something called the photoelectric effect, which describes how electrons are emitted from a metal surface when struck by photons of light. Now, there is a minimum frequency below which no electrons are emitted because they don't have enough energy to eject electrons from that metal. Above that frequency, the more intense or the brighter the light, the more electrons you have emitted. And at the higher frequency you go, the more energy those electrons have. But the key thing is there's a minimum frequency below which you don't get anything given off. And in case you're wondering about the term photon, that's a light particle. Light does have both wave and matter properties, which is why if you fire these particles, they can kind of cause these electrons to get bounced off. But don't get too bogged down in the weeds on some of these definitions. They're pretty unlikely to ask you anything about those two bullet points. What they would ask you is something like this problem, where it says in a certain element, it takes energy of 335 kilojoules per mole to eject an electron. Does a photon with a wavelength of 4.5 times 10 to the -7th meters have sufficient energy? So we need to do a little bit of math. So first of all, we know that the speed of light equals the wavelength times the frequency. So the speed of light is 2.998 times 10 to the 8th meters per second. And that equals 4.5 times 10 to the negative 7th meters times our frequency. So if we solve for frequency, we're going to take 2.998 times 10 to the 8th, and we're going to divide it by 4.5 times 10 to the negative 7th. And we're going to get a frequency of 6.66 times 10 to the 14th hertz. So that's our frequency. Then define the energy. Energy equals Planck's constant times the frequency. And Planck's constant is 6.626 times 10 to the negative 34th joule seconds times our 6.66 times 10 to the 14th hertz, or inverse seconds. And that's going to give us, if we multiply that by 6.626 times 10 to the negative 34th, I'm coming up with 4.41 times 10 to the negative 19th joules. Right? So that's how much energy a single photon has. Now you might say, well, that's way smaller than 335 kilojoules per mole. But we need to find not how many kilojoules per mole of electrons, but how many joules per electron. So first of all, 335 kilojoules per mole is the same as 335,000 joules per mole. And then we can multiply that by 1 mole is 6.022 times 10 to the 23rd electrons, so that we cancel out moles and we get joules per electron. So we take 335,000 and we divide that by Avogadro's number, and we get 5.56 times 10 to the negative 19th joules per electron, which, if we compare these two numbers, this photon is insufficient. So the answer is no. Now, alternatively, instead of converting kilojoules per mole to joules per electron, we could convert our joules down here to kilojoules per mole of photons. This is joules per photon. And then in 1 mole of photons, that we could multiply that by Avogadro's number. So we take the 4.41 times 10 to the negative 19th times Avogadro's number. And I'm coming up with 265,570 joules. Whoops, did not mean to do that. Sorry, I hit the wrong button on my screen. So that's coming up with 265,570 joules, or 265.570 kilojoules per mole, which, if we compare those two numbers, it's still insufficient. So that's a sample problem. You'll have a couple more sample problems in your assignment for today, just to kind of see if you can get the hang of a few of these problems. It's just two formulas. You have that speed of light equals frequency times Planck's constant, and speed of light equals frequency times wavelength, and then energy equals Planck's constant times the frequency. So if you have those two formulas, you should be able to kind of solve for what you're looking for. And then you just have to compare it to, are we considering a single thing, or are we involving moles? And we'll get more comfortable with moles in our next unit, which has stoichiometry in it. I wouldn't worry too much about this whole light having both wave and matter properties. That's not really going to be important for this. So this brings us on to the Beer-Lambert law, which you've already worked with at this point. It says absorbance equals molar absorptivity times path length times concentration or molarity. Absorbance is the negative log of transmittance. That's not particularly important for this. You're never going to have to calculate absorbance from transmittance. The LabQuest does that for you. Then you have your molar absorptivity constant, which describes how a particular substance absorbs light of a particular wavelength. So if you change the wavelength or you change the substance, you need a different molar absorptivity constant. Then B is the path length, and C is the concentration or the molarity. Right? And the path length definitely makes a difference, which we'll see in a couple minutes. Now, we can use a spectrophotometer where we shine a single wavelength to measure the transmittance, and then we calculate absorbance from that. It only works with colored solutions, and you need to select a wavelength that provides maximum absorbance. For instance, if you're working with a blue substance like this, you don't want to use blue light, because the reason this appears blue is because blue light passes straight through it. You're probably going to want to choose a different color, like for instance red, which is absorbed quite strongly by a blue solution. When you're using the spectrophotometer, or we use the cheaper colorimeters, you have to initialize with a blank cuvette, which is one that's just got distilled water in it. And you set your transmittance to 100% or your absorbance to 0. You just had to press the calibrate button. The path length is usually held constant. I mean, every single cuvette that we used in the labs that we did had a path length of exactly 1 centimeter, because the internal dimensions of this cuvette are 1 centimeter squared. And then you can make a calibration curve, which is a graph of absorbance versus concentration, and you use that to find the concentration of unknown solutions. So that's where you make a graph of absorbances at different concentrations, and then if you measure an absorbance of an unknown, you look on the graph and see what it is, or you do a linear regression calculation and do the math that way. Now I do want to show you, I have a second cuvette here. I don't know how well this is going to show up for you. Let me make this a little bigger. This cuvette over here, you may notice that in the bottom half of the cuvette, the solution appears to be significantly lighter in color. And that's because it has a path length down here at the bottom that's only half a centimeter. So this cuvette would be used if you have a very small sample, like if you only had just say 1 milliliter of your sample that you're able to collect, you would use a cuvette like this, and you would just adjust your calculations. The absorbances would all be half because of what they were with the standard cuvette, because your path length has been cut in half. So that's just a little illustration. You can see just within this one cuvette, the path length up at the top is 1 centimeter, and at the bottom, it's half a centimeter. I don't like to use these though, because our colorimeter takes the reading pretty close to this division right here. Ordering these was really a mistake on my part when we did that.